Wait till Heather gets back. Um, Interesting. I wonder what the issue is there. It's not me. Oh, Heather, can you hear me now?
Yeah, it's working now. I don't know what that was. Like it was unmuted and everything. Maybe it's just a
You're saying
glitch.
things I can't hear you.
Oh,
um,
hmm.
yeah, really audio issues apparently. Um, I'm saying words. If you can hear them, okay. I'm glad you can hear them. Cool. So if you want to say something, you might have to write in the chat because it didn't seem like I could hear you if you were trying to talk before. Um, I will leave the chat up so I can see it. So I was going to go ahead and start with a ratio test example first, or I should say a radius of convergence example, just to point out one thing I noticed from the homework. And then we'll talk about Taylor's formula and Taylor's theorem / formula. So let's look at the following. Let's say we want to find the radius of convergence, which we typically abbreviate as ROC, radius of convergence. For the series, the sum from n equals 1 to infinity of x minus 5 to the nth power over n plus 7 times 4 to the n plus 1. And so just like every other time we've done one of these radius of convergence questions, we're going to use the ratio test. I will actually, before I start with that, I will point out it's worth noting that the center of this series is just x equal to 5. I guess I should say c, but really you can call it c equal to 5. That's the center. And so then find the radius, we're going to do the ratio test. We're going to do the limit as n goes to infinity of our an plus 1 divided by an, which is going to be the limit as n goes to infinity of, so this n plus 1 term, so x minus 5 to the n plus 1 over n plus 1 plus 7. Let's just write n plus 8 times 4 to the n plus 1 plus 1 is n plus 2. And then times the nth term, the reciprocal of the nth term. So it's going to be n plus 7 times 4 to the n plus 1 over x minus 5 to the n. When we saw happening last week, which happens pretty much every time, is anything that's raised to a power of n ends up canceling relatively nicely. For example, x minus 5 to the n plus 1 divided by x minus 5 to the n is just going to be x minus 5. And similarly, the 4 to the n plus 1 over 4 to the n plus 2 is going to end up with a 4 in the denominator. So we're going to get an x minus 5 over 4. And then the n plus 7 over n plus 8, or the polynomial piece of this, ends up really being a non-factor. Because if you take the limit as n goes to infinity of n plus 7 over n plus 8, that limit's going to be 1. So this ends up equaling the absolute value of x minus 5 over 4. And we want that limit, using the ratio test, we want the series to be convergent. That limit has to be less than 1. Now, the easy way to answer this question is you've got x divided by 4, so the radius of convergence is going to be 4. So we can see the radius of convergence is 4. Now, on your homework with the Weber questions, I see that most of the questions kind of ask you to find the interval, but say don't worry about the endpoints. So if we can find the interval as well, we might as well. So we're going to have x minus 5 over 4 between 1 and -1. Multiply everything by 4, we get -4 less than x minus 5 less than +4. And we add 5 to all parts of the inequality, and we get -4 plus 5 less than x less than 4 plus 5, which is 9. And clearly, the center of this interval is 5. And the radius, the distance from 5 to 9 is 4, the distance from 5 to 1 is 4, or the total distance from 1 to 9 is 8, and half the diameter, half of 8, is going to be 4. So yes, I will point out the actual interval of convergence here is, yeah, it's going to be sorry, I have to think about this for a second. It would be inclusive of 1 and exclusive of 9. But we don't need to worry about that. As far as our answers are concerned, when we find the interval convergence on the Weber questions, you would just write it as parentheses 1 comma 9. We're not going to worry about what's happening at the endpoints because it's not something we talked about. Okay, so let's talk about Taylor's formula / Taylor's theorem. And here's what I'll say about it. There is a way to derive this formula. It's actually not terrible. It's not particularly necessary to do. I will remind you and people watching the video later that I did post on Canvas a video about the Taylor series by 3 blue, 1 brown, I think. It's a really nice video. It kind of delves into why we use it, why it works, and how it's nice. And there's lots of nice animation as well. So if you have the time, I would encourage you to watch it. I think it's great. So here is Taylor's formula. So basically, this is a way that for almost every function, there are some weird exceptions. For almost every function, it's a way to write the power series centered at some choice of C for almost any function. So the formula is as follows. We're going to say that whatever function f of x we're starting with is, it's going to be equal to, here's the long way of writing it. It's going to be f of c plus f prime of c plus f double prime of c over 2 factorial. Oh, you know what? I made a small mistake there. Apologies. Let's try that again. Sorry about that. Forgot something very important. It's f of c plus f prime of c times x minus c to the first plus the second derivative at c over 2 factorial times x minus c squared plus the third derivative at c over 3 factorial times x minus c cubed. And you can kind of see how the pattern goes. Every next term is going to be the next derivative evaluated at the center divided by the next factorial times x minus c to the next power. The condensed format is the sum from n equals 0 to infinity of the nth derivative, which we write as f superscript parentheses n of c over n factorial times x minus c to the nth power. That's how we write the Taylor's formula. And I believe last time in class we showed, or we found, that for e to the x, let's say f of x equal to e to the x, that the Taylor expansion or the Taylor polynomial was the sum from n equals 0 to infinity of x to the n over n factorial, which if you write out the terms would look like 1 plus x squared over 2 plus x cubed over 3 factorial, and so on and so on and so on. This is a reminder, we typically don't write divided by 0 factorial or divided by 1 factorial because 0 factorial is 1 and 1 factorial is 1. So we just omit those terms typically. So let's look at some other examples. Actually, let me see, where do I want to start? Let's look at, that's what's kind of gross. Let's look at something that's fairly typical. Yeah. So let's say we want to find, sorry, one second here. Find the power series for f of x equal to 1 over 1 plus x. I should say, pardon me, centered at 0. So usually the way this ends up working is we start finding a few derivatives of our function until we can maybe see a pattern. So I'm trying to make it easier to write our derivatives by first rewriting f of x as 1 plus x to the negative 1. And then the first derivative is going to be -1 times 1 plus x to the negative second. The second derivative is going to be, I'm going to not simplify, except for the sign. So instead of writing 2, I'm going to write 2 times 1 to make it a little bit more obvious what's going to happen. And I would say most of the time for these power series formulas, simplification is not your friend. It is better to not simplify the formula, so it's maybe easier to identify what the pattern actually is. So I'm going to write this next part as positive 2 times 1 times x plus, sorry, 1 plus x. It doesn't really matter, but be consistent. So the negative third. The third derivative is going to be -3 times 2 times 1 times 1 plus x to the negative fourth. And the fourth derivative is going to be +4 times 3 times 2 times 1 times 1 plus x to the negative fifth. And then if I'm feeling good about, like, I think I know what the pattern looks like, then I kind of try to go down to like the 10th derivative. So if I wanted to do the 10th derivative, well, I'm noticing that the odd ones have negatives and the even ones have positives. So it's going to be a positive. I think it's going to be 10 times 4. You know what I should say? Sorry, not 10 times 4. 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Instead of writing all that, I should just write 10 factorial. And that's going to be times 1 plus x to the negative 11. And then what I really want to do is I actually want to find, instead of just the derivative at any x, I want to plug in the center. So f of 0 is looking like 1. F prime of 0 is looking like -1. F double prime of 0 is looking like +2. The third derivative at 0 is looking like, I'm not going to write -6, I'm going to write -3 factorial. And the fourth derivative at 0 is looking like +4 factorial. And the 10th derivative is looking like, at 0 is looking like 10 factorial. So it looks like we're alternating, and what my goal really is to say, well, the nth derivative at my center is looking like it's going to be n factorial, except it's going to be positive when n is even and negative when n is odd. And the way we usually get that is by introducing a -1 to the nth power. And then checking to make sure if you plug in an even value like 4, -1 to the fourth is positive, and you plug in an odd value like 5, -1 to the fifth is -1. So this is definitely giving me the right signs. If it was off, I would add 1, make it like -1 to the n plus 1. So then we can say that the sum, sorry, I should back up there a little bit. We can say that our function f of x equal to 1 over 1 plus x, we can write it as the sum from n equals 0 to infinity of our nth derivative at 0 formula, which is just -1 to the n times n factorial, divided by n factorial times x minus 0 to the nth power, which we should certainly simplify. The n factorials do cancel, so we end up just getting the sum from n equals 0 to infinity of -1 to the n times x to the n, which I would probably leave like that, but some people, when you have two things multiplied together raised to the same power, you could choose to write this as the sum from n equals 0 to infinity of -x or -1 times x raised to the nth power. So what this looks like, if we write out the terms, is, well, -1 to the 0th is, sorry, -x to the 0th is 1, plus -x to the first is -x, plus -x squared, plus -x cubed. Oh, I should have had a minus sign there. Plus -x to the fourth, plus -x to the fifth, and so on and so on. So it looks very, in fact, it is a geometric series. It's -x to the nth power. So this shouldn't surprise us. And this actually kind of leads to something else that's really important. So when we're asked to find a power series, sometimes when we're kind of unlucky, we have to resort to using this long process and this formula. But a lot of the times what we're actually going to do is use some well-known series and kind of manipulate them. So I'm going to show you another way of finding a series that is typically what we would prefer to do if we have the choice. So here's another way. So here's what we want to keep in mind so far. Here are some well-known power series that we know we're going to add like maybe 2 or 3 more to this list. So keep in mind our list of well-known power series. Most of these are centered at 0. So the two we know so far are 1 over 1 minus x. That looks like a first term over 1 minus a ratio, and that was equal to the sum from n equals 0 to infinity of x to the n, which if you want to write out terms, it's 1 plus x squared plus x cubed plus x to the fourth forever. And I will point out that the radius of convergence is r equal to 1. Because for a geometric series to converge, the ratio has to be between -1 and 1. And then the second one we have is the one we just did on the previous page, which was that e to the x is equal to the sum from n equals 0 to infinity of x to the n divided by n factorial. And that's 1 plus x squared over 2 plus x cubed over 3 factorial plus x to the fourth over 4 factorial and so on. We're going to add to this list later, so I'm going to keep this paper off to the side and I'm going to come back to it. So you might want to make yourself a little area to write these down because they do come up often. All right, so what we're going to do is instead of writing up this whole formula like we did here, the alternate way is to say, well, I see that the function I'm looking at, f of x equal to 1 over 1 plus x, looks an awful lot like one of the geometric series that I already, sorry, one of the power series functions I already know the formula for. So I'm going to try and make this look like 1 over 1 minus x. So I'm going to say, well, 1 over 1 plus x looks like 1 over 1 minus negative x. And then I know that basically 1 over 1 minus a thing looks like the sum from n equals 0 to infinity of just whatever that thing is raised to the nth power. When it was the previous formula, it was 1 over 1 minus x, and it was the sum of x raised to the nth power. But now it's 1 over 1 minus x, and we can say that's going to end up being the sum from n equals 0 to infinity of minus x to the nth power, which is exactly what we got doing it the longer way. So this is a pretty common tactic that we use a lot when we're doing problems like this. For example, if we wanted to find, say, sorry, I figured I have to write the words here. So we want to find the power series for 2x over 1 minus x squared. Well, there's two things I'm going to do. One, I don't want to write 1 here. So first of all, I'm going to look at 1 over 1 minus x squared. And I think of that as just 1 over 1 minus a thing. And 1 over 1 minus a thing is essentially the geometric series formula. It's your first term over 1 minus your ratio. And so we can think of this literally as 1 plus x squared plus x squared squared plus x squared cubed, and so on and so on. Which, yeah, we could write the summation notation for. We don't really need to at this point, but I will anyway, because why not? So you write it as a sum from n equals 0 to infinity of x squared to the n, or you can simplify that as x to the 2n. And then I really want 2x times 1 over minus x squared, so I'm just going to multiply everything by 2x. So 2x times 1 over 1 minus x squared is the same as 2x over 1 minus x squared. And I'm literally multiplying every one of these terms by 2x. So it's going to be 2x times all of this. Which, to kind of see it more nicely, like if we actually distribute the 2x, we get 2x plus 2x cubed plus 2x to the 5th plus 2x to the 7th, and so on and so on. And what we're really doing is, with this x to the 2n, we're just multiplying each one of those x to the 2n's, x squared, x to the 4th, x to the 6th, by 2x. So we're really getting the sum from n equals 0 to infinity of 2x to the 2n plus 1. Right, we're taking this x to the 2n, right? That's what that is. And we're just multiplying it by 2x. And 2x times x to the 2n, well, you add the powers, and 2n plus 1 is 2n plus 1. And if you start writing out terms, it totally works. If n equals 0, you get 2 times x to the 0 plus 1, which is 2x. If n equals 1, you get 2 times x to the 2 plus 1, which is 3. Oh, right there, n equals 1. If n equals 2, 2 times 2 is 4, 4 plus 1 is 5, you get 2x to the 5th, which is exactly that term there, and so on and so on and so on. So a lot of the time, we would prefer to find the power series by manipulating a well-known series instead of appealing to Taylor's formula. Taylor's formula is still great because it kind of is always there in the background available to us. But if we can, we would kind of much rather do it this quote unquote easier way. And I will mention this way is really easier. If you were to start with 2x over 1 minus x squared, the derivative is centered, and I should say, you know what, I didn't specify here, and I should have said find the power series for 2x over 1 minus x squared centered at c equal to 0. Typically, if we forget to mention where a series is centered at, we usually mean centered at 0. But if we were trying to do this one the long way, it gets messy really fast. Let me show you what I mean. So if you're trying to use Taylor's formula, well, the derivative, so I'm going to start with 2x over 1 minus x squared. I'm probably going to write it as a product. I have f of x equal to 2x times 1 minus x squared to the negative 1. And things are going to get terrible fast. The first derivative, I'm going to use the product rule and get 2 times 1 minus x squared to the negative 1 plus 2x times negative 1 times 1 minus x squared to the negative 2 times the derivative inside, which is negative 2x. So it's going to be a positive 2x times 1 minus x squared to the negative 2 times the negative 2x, but I already dealt with the negative sign, times another, no, I guess I dealt with the 2x already, right? It was a, sorry, so I have my 2x, then I have my negative 1 times 1 minus x squared to the negative 2 times the negative 2x. Okay, yeah. That was just the first derivative. If we keep doing this, things are going to get out of control really quickly because we're going to have the derivative of this, and then we have to have a product rule here, and we're just going to get product rules on product rules on product rules, and it's going to get out of control. So this is a great example of why we wouldn't want to use Taylor's formula if we can do it a different way. Let's look at some more kind of classic examples of things that come up pretty often. So let's try and find the power series for f of x equal to sine of x, also centered at c equal to 0. Well, one last thing on the previous example that I forgot to mention was that this series here also has a radius of convergence of 1. You could, what should I say here? Since it looks very similar to 1 over 1 minus x, it probably has a similar radius of convergence, but we actually could use the ratio test, right? If we use the ratio test, we're going to see that well, in fact, we can see what our ratio is, right? If you look at our series here, our ratio is for sure x squared. 2x times x squared is 2x cubed. 2x cubed times x squared is 2x to the 5th times x squared is that. So you could also use the ratio test, but it's going to yield the same result. The limit is then goes to infinity of our 2x to the 2 times n plus 1 plus 1, that's our an term, over 2x to the 2n plus 1 in absolute value. If we simplify that, it's the limit as n goes to infinity of, let's see, the numerator here is 2n plus 2 plus 1, which is 2n plus 3, and x to the 2n plus 3 divided by x to the 2n plus 1. 2n plus 3 is 2 larger, so it's really just x to the second. And 2 divided by 2 is 1. So really just left with the limit as n goes to infinity of x squared. Fun fact, when you do this ratio test and all the things with n's cancel, it means you actually had a geometric series to start with. Our ratio is actually x squared. It's not just acting like x squared eventually. So that means we can really do without the limit as n goes to infinity. And we want the absolute value of x squared to be less than 1, which means that x has to be between -1 and 1. So it really is indeed geometric. And the interval of convergence is -1 to 1, which means the radius of convergence is indeed R equal to 1. We usually use a capital R when we're writing with the radius of convergences. All right. So now let's go look at that sine example I was talking about. So yeah, good. All right, cool. So power series for f of x equals sine of x centered at c equals 0, and we will also find the radius of convergence. So let's start writing down some derivatives, which are not too terrible for sine. So f of x is equal to sine of x. Our first derivative is cosine of x. Our second derivative is negative sine of x. Our third derivative is negative cosine of x. And then things just start repeating. The fourth derivative is positive sine of x. The fifth derivative is cosine of x. So you can even say, right, this is equal to the fifth derivative. This is equal to the sixth derivative, equal to the seventh derivative, equal to the eighth derivative. And I think we can kind of stop writing things down. And then we can see that f of 0, which is the center, is sine of 0, which is 0. F prime of 0 is equal to cosine of 0, which is 1. F double prime of 0 is equal to negative sine of 0, which is also 0. F triple prime of 0 is equal to negative cosine of 0, which is negative 1. And then the pattern just starts repeating. The fourth derivative at 0 is 0. The fifth derivative is 1. The sixth derivative is 0. So it looks like every even derivative is going to be 0. And every odd derivative is going to oscillate back and forth between positive 1 and negative 1. So let's write out some terms. I always would prefer, almost always would prefer to write out terms as opposed to just trying to go straight to the generic formula. So I'm going to say that sine of x centered at 0 is equal to, well, my first term is, well, actually 0. Plus, then it's going to be my f prime of x, my f prime of 0 is 1 times x minus 0 to the first power over 1 factorial. Okay, I didn't write any of that because it's all ones. Plus, then my f double prime of 0 is 0 over 2 factorial times x minus 0 squared. I don't really need to write the x squared because it's not going to make a difference, but I guess I could write all that. And then my next term is going to be plus negative 1 over 3 factorial times x minus 0 cubed. And then I'm not going to get an x to the fourth term, I'm going to get 0x to the fourth. And then I'm going to get a positive 1 over 5 factorial times x to the fifth. And so we can start to see an emergent pattern. We see we're getting every odd power of x and the signs are alternating. I should say every odd power of x, x to the first, x to the third, x to the fifth, divided by that same number factorial, but it's alternating signs. So the next term I expect to get is going to be plus negative 1 over 7 factorial times x to the 7th, and then plus positive 1 over 9 factorial times x to the 9th, and so on and so on and so on. So trying to write this formulaically, it's a little interesting. We're going to say it's the sum, in fact, the sine of x is equal to the sum from n equals 0 to infinity. So we only want the odd powers. So what we're going to do is we're going to write x to the 2n plus 1 power. Because 2n plus 1 gives you back an odd number every time n is an integer. So if n is 0, 2 times 0 plus 1 is 1. If n is 1, 2 times 1 plus 1 is 3. And every time n increases by 1, this increases by 2. And then we want the same number factorial. And then we also want a negative 1 to the nth power so that we alternate signs and we start with a positive sign. And if you write this out, this is indeed equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so on and so on and so on. And that should definitely go on your list. Before we write it on the list, though, I'm going to do one other one. So we could do the same thing to find cosine, but we could also use a trick. I don't think we actually learned this in 16C about how, so the trick is that you can actually find other power series by differentiating or anti-differentiating a known power series. And I don't know if that's something we talk about in 16C, but we can do it for one example here. So we take the derivative of sine of x. Well, the derivative of sine of x is equal to cosine of x. And we take the derivative of this side here, I'm gonna get the derivative of x is 1. The derivative of x cubed over a constant is 3x squared over that constant. The derivative of x to the 5th over a constant is 5x to the 4th over that constant. And so on. Oh, sorry, that should be a plus, not a minus. And then a minus 7x to the 6th over 7 factorial, a plus 9x to the 8th over 9 factorial, and so on. But 3 over 3 factorial, the 3's cancel, and you get a 2 factorial. So since it being 1 minus x squared over 2 factorial plus 5 over 5 factorial, the 5's cancel, and you get a 1 over 4 factorial. So you get x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial, and so on. So sine and cosine have very similar patterns. Not surprising, they're very similar functions. And they're either all the odd powers alternating divided by their respective factorials, or for cosine, all the even powers divided by their respective factorials alternating. So let's write those down over here real quickly. So the two more that you should probably know by heart is that sine of x is equal to the sum from n equals 0 to infinity of -1 to the n x to the 2n plus 1 divided by 2n plus 1 factorial, which is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so on. And cosine of x has a very similar expression. Cosine of x is equal to the sum from n equals 0 to infinity of -1 to the n times x to the 2n over 2n factorial, which does start with a 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and so on and so on. Oh, and we said we talk about the radius of convergence here. So let's talk about the radius of convergence. So the radius of convergence for f of x equal to sine of x, which again is the sum from n equals 0 to infinity of -1 to the n x to the 2n plus 1 over 2n plus 1 factorial. Something I have noticed over the years is that when you have an expression like this and you still end up having the factorial in the denominator, so I will point out we don't have that factorial in the denominator for this geometric series or for this power series here, but these three all do. The radius of convergence typically ends up being infinity, and let me show you why. To define the radius of convergence, again, ratio test. So we're going to take the limit as n goes to infinity of a sub n plus 1 over a sub n, which is the limit as n goes to infinity. Okay, let's make this not too terrible. So I'm going to write the negative ones, but you can actually kind of ignore them. Talk about why. So -1 to the n plus 1, x to the 2n plus 1, or sorry, 2 times n plus 1 plus 1. We'll point out that that is 2n plus 3. Divided by 2n plus 3 factorial times, oops, no, that's fine. I'm not making a mistake. I thought it was for something. Times the reciprocal of this, which is 2n plus 1 factorial over -1 to the n, x to the 2n plus 1. Here's how things are going to simplify. We're going to get the limit as n goes to infinity of the absolute value of, okay, the -1 to the n plus 1 divided by -1 to the n is just -1, but a -1 times a bunch of stuff in an absolute value actually doesn't matter, so we're just not going to write it. The x to the 2n plus 3 divided by x to the 2n plus 1 is going to be x squared. And then the 2n plus 1 factorial over 2n plus 3 factorial, we're going to write it as 2n plus 1 factorial over 2n plus 3 factorial is 2n plus 3 times the next smallest integer, which is 2n plus 2. And then we have times 2n plus 1 times 2n times, right, all of the terms for 2n plus 1 factorial. So, oh, sorry, absolute value, not a bracket, sorry. And these two factorials, the 2n plus 1 factorial and the 2n plus 1 factorial, cancel out. So we're left with the limit as n goes to infinity of x squared over 2n plus 3 times 2n plus 2 which is definitely going to be 0, no matter what x is. Pick x equal to 1,000,000. 1,000,000 squared is 1,000,000,000, and 1,000,000,000 divided by something that's getting infinitely large is eventually getting super duper small. So that limit is always less than 1, which means no matter what we pick for x, this series converges. So our interval of convergence is all real numbers, which I would typically write as the interval from -infinity to infinity. And our radius of convergence is r equal to infinity. And that's true for sine and for cosine. Excuse me. There is a theorem that, again, I don't think it's taught in this class, but I'm going to mention anyway, that if you take the derivative of a series or the antiderivative of a series, it has the same radius of convergence as the original series. So we saw before last class that e to the x has a radius of convergence of r equal to infinity. It converges for every value of x, and so do sine and cosine. We just showed that sine does. And we could show it for cosine, or you could show it for cosine on your own. Or we could say, well, we know that sine, the derivative of sine is cosine. And when you differentiate or anti-differentiate a series, the radius of convergence does not change. It's pretty cool, actually. It's a neat theorem, I think. The radius of convergence here is r equal to infinity as well. So here is why I think this is kind of neat. Useful even. So someone could then ask us to, for example, find the power series for sine of x cubed. Well, as I mentioned before, the power series for something more complicated like this is going to get gross fast if we use Taylor's formula. Here's why. And again, centered at 0. Look what happens if I start taking derivatives. So f of x is sine of x cubed. Derivative is cosine of x cubed times 3x squared. Second derivative is, see, derivative cosine of x cubed is negative sine of x cubed times 3x squared times the other 3x squared, plus then cosine of x cubed times the derivative of 3x squared, which is 6x. And I think you can see where I'm going with this. After the second derivative, things are just going to get super duper gnarly. This is, that's 9x to the 4th. The derivative here is going to be, let's see, negative cosine of x cubed times 3x squared times that 9x to the 4th plus negative sine of x, oh gosh, times to the 36x cubed. And then, no, I shouldn't do this, right? This is going to get awful really fast. But what's great is we know how to do this, or we're about to see how to do this. So from before, we know that sine of x, I'm actually not going to write in the x there. Sine of x is equal to, I should say, sine of x centered at 0. Its power series is x, which I'm not going to write, minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so on and so on. But you don't have to write x there. You can fill in any expression you want, and it's still valid. So sine of x cubed is equal to x cubed minus x cubed cubed over 3 factorial plus x cubed to the 5th over 5 factorial minus x cubed to the 7th over 7 factorial, et cetera, et cetera, et cetera. And we can write this as the sum from n equals 0 to infinity of, instead of -1 to the n times x to the 2n plus 1 over 2n plus 1 factorial, we can replace the thing that's in the parentheses with x cubed. So it is correct to say that the power series for sine of x cubed centered at 0 is the sum from n equals 0 to infinity of -1 to the n times x cubed to the 2n plus 1. If I multiply those powers together, I get x to the 6n plus 3 over 2n plus 1 factorial. And this is extremely useful, right? It's so much more convenient to do it this way. And it's actually useful because then someone could say, well, great, I want you to use a sure, the 15th degree. It just means the highest power. Taylor polynomial to estimate the integral from 0 to 1 of sine of x cubed. Which is kind of nice because sine of x cubed, I'm pretty confident, is impossible to actually find an antiderivative of. So this is an example of where Taylor polynomials are actually really useful in helping us calculate things that we wouldn't otherwise be able to calculate. Sure, there are other ways of approximating integrals, like using trapezoid rule or the midpoint rule, or I don't think we talk about Simpson's rule, but there are other methods of estimation. But this is a very good method of estimation. So we could say, well, great. Let me write it up here. I think I fit it up here. Yeah. So we can say, well, sine of x cubed, these first three terms go up to the 15th power. So we can say the integral from 0 to 1 of sine of x cubed dx, we can say is approximately equal to the integral from 0 to 1 of x cubed minus x cubed cubed, which is x to the 9th, over 3 factorial. 3 factorial is 6. And plus x cubed to the 5th, which is x to the 15th, over 5 factorial, which is 120. And then we could actually anti-differentiate, which is super easy because they're all just power rule antiderivatives. So we're going to get x to the 4th over 4 minus x to the 10th over 60 plus x to the 16th over 16 times 120 is, I don't know, 1600 plus, I should know, 100, 16 times 12, James, is 192, right? Yeah. So it's gonna be 1,920. Yeah. From 0 to 1, and then you would plug in, and you just get, plugging in 1, you get 1/4 minus 1/60th plus 1 over 1,920 minus 0 plus 0. And that's probably, I don't actually know because I don't have a calculator on me, but it's probably actually a pretty decent approximation of the integral of sine of x cubed. You know what? I think Desmos will actually tell what it is. Let's see if Desmos will tell us. So one quick here. So let's see here real quick. Like if we pull up Desmos, we can do an integral by typing int, and then you can put in your limit of integration. Going to be, whoops, let's get down there. Whoops, 0 and to 1. And then we have sine of x to the 3rd. Let's see if it gives it to us. Nope, it does not give it to us. Oh, I need a dx probably. Maybe that's the mistake. Yeah, cool, 0.233. And let's see what our let's see what our approximation was. 1/4 minus 1 over, it's kind of neat that you can use Desmos like as a calculator, minus 1 over 60 plus 1 over 1,920. Yeah, that's a pretty good estimate, I think. I'm pretty pleased with that. So this is something that is, again, I'll say, like a lot of times you feel like, what do we actually use this math for? This is something that you can actually use a Taylor polynomial for, is to approximate the integral of something that we otherwise would not be able to anti-differentiate to a pretty good degree using only 3 terms of the series. So pretty nice. And this kind of idea of being able to find a power series using this kind of substitution idea where you take a known power series and replace the things you have with the things you want is very pervasive and we use all the time. So another example of this is trying to get a Taylor series for e to the negative x squared, because that's a very important function in statistics. So we say, well, the power series for e to the negative x squared is, well, we take f of x equal to e to the x, which is just the sum from n equals 0 to infinity of x to the n over n factorial. And we basically just replace the x with negative x squared. So then e to the negative x squared is going to be the sum from n equals 0 to infinity of negative x squared to the nth power over n factorial. I really do like replacing the x with just an open parentheses or an unfilled parentheses, and then filling in whatever I want to go there. I want that, I want that. And if we want, we can rewrite this as the sum from n equals 0 to infinity of -1 to the n times x to the 2n over n factorial. I think it's 158. So there's probably maybe one more power series on my list that comes up, but we can save that until next time. I hope this was illuminating, and I will see you on Friday. Have a lovely rest of your day. Let's figure out how to end the Zoom meeting. Bye, Heather. You're welcome, of course.